Okay, this video is the solutions to exam number 2, problem number 1. Okay, so in problem number 1, we are looking at an FFT, and we're given that it's 12,000 samples per second. You take 128 samples of the signal and zero pad to a length of 1024. All right. The X and Y values in the plot indicate the XY coordinates, just like the data cursor in MATLAB. So really this X value of 111 tells you what the peak is along the K axis. So those are really K values coming back out. And of course, these are the amplitudes that you read across for the peaks. So I think that's pretty straightforward. All right, so the question is, the first one, how many tones are present in the signal? All right, and so what we see here is 4 tones, but what we know is that FFTs are symmetric about n/2. All right, and so this first half of the FFT gives me all the information that I need. The rest of this is really just, if you remember from the sampling theorem, this is just the first replica showing up. Okay, so we know that there's 2 peaks here, therefore there's 2 tones. All right, the next question asks, estimate what the frequencies of these tones would be. All right, and I've told you the way I remember that is I take a ratio. The peak that we're looking for, F1, is to Fs as the K value is to the length of the FFT. All right, so you set up that little equation by just remembering that ratio. Okay, from there you know what Fs is. You can solve for the 2 frequency values. Remember the K value for the first one was 111. The K value for the second peak was 282. So that's where this number comes from. All right, next you're asked, look at the relative amplitude difference here. And if you're given that the strongest tone has a 1 volt amplitude, what is the amplitude of the weaker tone in volts? All right. So we know the way that dB works. You take the ratio. So that's why I took the ratio of the unknown A2, unknown, divided by what's known. We know that's 1 volt. So had that been 2 volts, the 2 would have gone there. You know, a 2 would have gone there instead of a 1. All right, so then we just use the definition of dB. We know the difference between the peaks. The question might come up, how do you know which order you should go in? Well, I know A1 is stronger than A2, so I should get a negative value for this number. All right. So then when I plug in 10 to the minus 6/20 is 0.5. If I had put a plus 6 there, I would have gotten a gain instead of a reduction. Okay, so the last question of problem 1, is can we rule out the rectangular window when we look at this FFT? I remember FFTs in general, you have to window the data to get access to the data. We don't have infinite length computational power. So if we use a rectangular window, the side lobes are down by about 13 dB. And so we can kind of guess here, this side lobe is down more like 30 dB. Okay, because it's down further, we know it's not the rectangular window. It's also not the Hamming window. The Hamming window is 40 dB. Turns out, I think I told you, I misspelled that window shape. There's also a window shape called the Hamming window. And you can see why that'd be confusing. The Hamming window has about 30 dB of attenuation of the side lobes. Okay, so there's the solution to problem number 1 of exam 2.